Our first speaker this morning is Kristopher Klein. He's assistant professor at the University of Arizona in the Department of Planetary Sciences and at the Lunar and Planetary Laboratory. He studies basic processes of plasmas with a focus on transport and dissipation in space and astrophysical systems. So without further ado, I would like to hand over to Chris.
Thank you very much for both the opportunity to speak and for all of your time and listening to this, my talk. I'm going to make sure this is showing and we'll go ahead and get started. So this, first of all, is the work of many people doing many different parts of the project. So I want to thank many of the people, including some of your colleagues that have enabled the observational aspects of this primarily theoretical interpretation, interpretive work, including the outstanding work that's been done recently by both the SWEEP and Fields science teams, which we'll loop back to at the end. So what are we looking at here? Because this is such a diverse, broad group of people studying cosmology, galaxy formation, planets, as well as plasmas. I wanted to make sure that we're on the same page about the physical system that we'll be focusing on for the next 24 minutes. So we're going to be talking specifically about understanding dynamical processes in the solar wind, which is our sun's hot but tenuous atmosphere that extends out and forms a bubble that fills our solar system, the heliosphere. Now, this is an important system to study in and of itself, but it also serves as a wonderful natural laboratory for studying a plethora of different universal processes. Effectively, if you send spacecraft up and you record for long enough periods of time, you can find plasmas that have different characteristic features. For instance, say the balance between the thermal and the magnetic pressure, parameterized as the proton plasma beta in this probability distribution diagram. This is drawn from several decades worth of observations in the near-Earth environment at 1AU, and we see most of the time the thermal and magnetic pressures are about the same, but if you wait long enough, you will get hours upon hours of measurements of very high or very low beta plasmas, which means that if you really care about, say, an accretion disk where you have very strong magnetic fields, you'll be able to model at least some of those plasma parameters that are driving the dynamics by studying the solar wind. And you can pick your other favorite plasma parameters and use this as an excellent natural laboratory for studying those processes. We're going to be talking specifically about understanding the coupling between the thermal particles as to the electric and magnetic fields. And so if we want to be able to do that, we need to get good local measurements of the VDF as well as the electric and magnetic fields, something which we don't have direct access to if all we're doing is measuring photons from very distant sources. So this is another one of the wonderful advantages that we can have by actually doing studies of these local solar processes. And what we see when you actually take pictures of the local VDF is not a simple isotropic Maxwellian. It's not the same kind of single temperature gas that we're all breathing in right now, but instead you see something like this figure, which comes from a measurement made by the Helios spacecraft at about half the way between the Earth and the Sun. And each of these different contours are demonstrate the probability distribution function, the velocity distribution function. And we see that it's not nice, simple circles, which would represent that isotropic distribution. Rather, the width of this distribution, transverse compared to parallel to the magnetic field, which is drawn as this dashed line, are quite different. They're said to be a temperature anisotropy. But you also see a number of other structures in there, in this case, this secondary proton beam. And all of these different features will couple to the local electric and magnetic fields. And so by getting these local measurements, we can better understand that kind of coupling, which is, again, a potentially universal process. Now, we're going to focus on understanding the different kinds of waves that these departures from local thermodynamic equilibrium can actually draw. These have been studied theoretically for, well, more than half a century now, and can be very broadly broken into different classes, either fluid instabilities, where the total macroscopic quantities, things like the excess parallel pressure, prevent restoring forces from turning a small perturbation into a damped perturbation, but instead growing wildly like a fire hose wiggling around when the parallel pressure is much larger than the total perpendicular pressure. That's this well-known fluid or CGL fire hose instability illustrated in this cartoon in the center, but also depending on the local shape of the velocity distribution function, specifically the gradients in velocity space of that f, this actual measured structure right here, different electromagnetic waves traveling at different speeds will resonate with different parts of the distribution, and in doing so can either damp away through processes like Landau or cyclotron damping, or actually give some of that free energy to the local fields, leading to the production of these unstable waves. So we're going to try to understand how common these different processes are, and if they play any important role in the dynamic evolution of the solar wind, or if they're just some filigree sitting on top that aren't actually essential for understanding the basic physics. So the first thing we want to do is understand, well, how common are these? Did Marsh simply cherry pick that one event? And most of the time we do have isotropy. Well, one of the things we can do is take those decades worth of observations and look at different measures for the departure from local thermodynamic structure. Here are, need to pretend there's not a screen behind me, but instead in front of me. Here are three different measures: the temperature anisotropy of the protons, T perp over T parallel, the temperature disequilibrium between the alphas and the protons, as well as the relative drift between the different ion components. In this case, it's the drift between the alphas and the protons normalized by the local alphane velocity. So we've taken those decades worth of data and we've organized it, we've column normalized it as a function of two different parameters, either the solar wind speed or this other quantity that we refer to as the Coulomb number. This Coulomb number effectively parameterizes how much a particular parcel of plasma has been processed by collisions since some distant point in its past, effectively taking the Coulomb collision frequency or some proxy for it, multiplying it by the distance that parcel has traveled, and then normalizing by the solar wind speed. And what we see is that there are regions of relatively collisionless plasmas that have very strong beams and have very significant differences in temperatures between the alphas and the protons. But as the collisions play a more and more significant role, that temperature difference decreases and that beam structure also begins to erode away. So clearly there is some weak collisional processing, but for a significant number of these intervals, there are significant sources of free energy that can act as reservoirs to actually drive this unstable behavior. So the next thing we need to do is try to model when do we exceed instability, add those are predicting when these waves should arise. And so people typically do that measurement made by Helios as much as can. In this case, they ignore that and instead just treat it as a single bi-Maxwellian distribution. I just got a signal my internet was unstable. Could I get a thumbs up that I'm still coming through?
Yeah, just about, but it's okay now. It's good.
What they will then do is say, okay, given this measurement of the temperature anisotropy, the difference in widths, can we come up for a single instability what the best value for a formula like this is? When you're above that threshold, we'll say the system is unstable, and when it's below it, we'll say it's marginally unstable. So one can take linear theory, plug a lot of equations together, and find a value for A, B, and beta naught for each of the different thresholds associated with this particular source of free energy. And when you compare the actual observations of the solar wind, in this case, those same, you find that some of those thresholds do a fairly good job of actually distribution of these points. And thus you could say, well, maybe these actually don't kind of as blocks much further out. But these parametric models do not account for other sources of energy. They don't account for this beam out there. They don't account for each of the components having different anisotropies. So one can attempt to build different fluid parametric models, effectively accounting for all of the free energy parallel. So in this case, the excess parallel pressure minus the excess perpendicular pressure, all drawn together. We're including the impact of the total parallel drifts. And then when using these thresholds, again, using that same set of multiple decades of data, we see that none of a very small fraction of the data actually surpasses this threshold. But again, this is only accounting for those fluid instabilities. This does kinetic, which requires the development of a different, and that tool that we use the 10 minutes talk. What we do, given a linear dispersion, that much of the kinetic physics as put into. Yes, hopefully it's coming through again. Thumbs up.
So yeah, so we can just it's just about hanging on.
Okay.
I was keeping it going because we can just about make out. Yeah.
Got it. Okay. I do apologize.
No problem.
So we are trying to use we're trying to determine if a particular equilibrium is stable or unstable. And so to do that, we return to our wave equation. So in this particular case, we've linearized the system and we've determined what is the current that is carried by each component and how is that associated with the linearized electric field. All of the physics there is bundled together into that epsilon, that dielectric tensor, which is a sum of each of the individual susceptibilities. And given all of that physical complexity, one can determine both the determinant of this D and where that's equal to 0 are the non-trivial complex valued solutions to the wave equation. Just to illustrate that, if you plot as a function of the real and imaginary components of the frequency, if you plot those, I've highlighted here in red where the actual solutions to this dispersion relation are. You can slowly vary the underlying parameters, in this case, varying the temperature anisotropy from 1 to 0.6 to 0.4, and you see some of the modes go from being marginally stable to going marginally unstable. And in theory, you can do that. You can hand trace all of these modes out for as complicated of a system as you want to. But given all of those different sources of free energy that I've laid out, that can be a very arduous task and one that isn't easily generalizable. And so for that reason, we have turned to the automation of a well-known technique, something called the Nyquist instability criteria. So instead of manually searching for all of these normal mode solutions, we perform a numerical contour integral over the upper half complex plane of 1 over our dispersion relation. And by doing that, because we know where the dispersion relation is equal to 0 is a solution, 1 over that is a pole of this complex valued function, which means if you do a contour integral and you have a non-zero integer, that tells you that there is an unstable solution supported by this particular equilibrium. Effectively, we're integrating around this circle, and if there's any red dots inside of that circle, we get a value of 1 or maybe more than 1. If there are no red dots, if there's no unstable modes, we get a winding number of 0, and we know the system is stable. Now, integrating at gamma equals 0 is informative, but not particularly useful. We don't care if something is growing at a rate that is slow enough that it's some fraction of the universe's age. So instead, we iteratively repeat this process by slowly raising up the contour until we transition from a point where we have an unstable system to a point where we have a stable system. And in doing so, we can robustly determine what the maximum growth rate is. So this gives us just an overall description of this actual analysis method. We take measurements of the solar wind, where we actually locally characterize the beta, how hot the system is, and all of those different sources of free energy that we can reliably observationally extract. And we calculate what the maximum growth rate supported at a particular wave vector is. And that's schematically what's drawn in each of these plots, looking as a function of both k-perp and k-parallel. Gray, the system is stable at that wave vector. The color, the system is unstable at that wave vector. We can then pick out what the fastest growing mode is, and in doing so, also determine all of the eigenfunctions associated with that mode, including how much power is being absorbed or emitted by each of the components. So we can actually dive down and say, well, this particular instability is being driven by the alpha beam, and the proton core is trying to stay, but in that's a general description of the method. We've applied it to a number of different, particular applied it to the as kind of a test case where we 100 or so nominal spectra and found that over 50% of them were found to be unstable. If you plot the intervals as a function of both beta and temperature at anisotropy, which is one of the favorite reduced parameter spaces people like to use, we see that not only are intervals that are beyond those typical thresholds are unstable, but a significant fraction of the intervals that are in the quote unquote stable regime are actually relatively strongly unstable. And this is because our model here accounts for all of the different sources of free energy, all of the other anisotropies, all of the beams, all of the free energy in those relative drifts, which drive a significant amount of this actual wave behavior. So we've gone ahead and actually also applied this not to just a few hundred, but also thousands. And now we're actually working on a data set of over 1 million from those characterizing uh, the sun and Earth. But I'd like to focus of my observation. I've been working from the probe project. So those of you not familiar, probe is a mission that has been slowly working its way closer and closer to the sun through a series of Venus encounters, so that we're actually measuring the local plasma environment and working on tracing the flow of energy as it heats the corona and then accelerates the solar wind outwards. A number of your colleagues are deeply involved with this mission, so I'm not going to attempt to detail all of their work right now, but please do inquire if you're interested in the data. Either reach out to me or members of the team here at SAO. I'm going to instead focus specifically on trying to understand one of the phenomena that we've seen from the first sets of encounters. That is the ubiquity of these ion scale waves. Now, these kind of wave storms have been seen at 1AU, but they seem to be incredibly prevalent when we look at in the Parker Solar Probe database. This eye chart right here is looking just at the magnetic field data, but what we're seeing is this structure, this extra energy in the magnetic field spectra that arises at frequencies associated with ion scales. And if you look at the handedness of this, if you look at the helicity, you see that it is primarily one or another handedness, which is associated with some sort of circular, at least elliptical wave that's moving around at those scales. And so that's exactly the kind of wave that could be driven by these resonant instabilities. So we're going to focus in particular on a few hour intervals and treat them using the span measurements of the local proton velocity distributions, which are illustrated at right here, where we treat it as either a single bi-Maxwellian distribution or as a combined core and beam profile, which will both have the same densities and total pressures, but have very different velocity space structure. This is a result that's been recently accepted in AppJ, and it's available in arXiv if you want more of the details, or I can send you a copy of the manuscript if you're interested. So what do we see when we apply this tool? Well, we see that for the two-component model, when we separately consider the beam and core, we get very robust instabilities for this first interval. The region of wave vector space in this top plot we see that is unstable is relatively wide, and the growth rate is relatively strong. We're talking 1/100th of an inverse cyclotron time. When we model it as a single component, it is still unstable, but the growth rate is nearly 2 orders of magnitude suppressed compared to the two-component model. And we can understand that by looking at where these waves are actually resonantly interacting with the distribution. And we see that if you treat it just as a single model, you're not properly capturing the DFDV structure correctly, and therefore you're misrepresenting the resonant structure and therefore the appropriate growth or damping rates. So this is a single 30-second measurement of the data. We can redo this for the entire hours that we have these good measurements for. And this top plot right here is showing what the growth rate is as a function of time during this first interval. And we see again that we have a very strong mode that's actually being generated during that entire interval. If we model it with that simpler single component, the stability is significantly reduced. But importantly, the same kind of wave is being driven in both cases. In this case, it's a fast wave that is coupling to the beam component. Yes, 3 minutes. Got it. However, I want to point out that including the beam does not always enhance the growth rate. For a different interval, when we do the same kind of analysis, again, the blue is when the beam is explicitly considered, we see that the growth rates are actually fairly comparable, and that when we include the beam, we actually get this oscillation back and forth between a parallel and an oblique instability, depending on the relative temperatures and densities of the beam as a function of time. So capturing that velocity space structure is really, really important to do, but does not universally enhance the growth rate. Importantly, the time scales at which these things are actually growing can be significant. We can effectively renormalize the calculation, different time scales. I'll draw your attention just to panel C right here. And what we see is that if you renormalize the growth rate to an estimate for how quickly energy is non-linearly being transferred through via some sort of turbulent cascade, for one of the intervals, when modeled as a two-component model, the transfer of energy is happening almost at the same rate as the instabilities are growing, indicating that these are not necessarily a subdominant process, but may play an important role in the actual dynamic evolution of the system. Now, just to wrap things up, all of these measurements I've been talking about thus far have been made at a single point in space, which means that we haven't actually been able to track how the wave is growing as a function in time. a mission that's currently in a phase A study is to not launch just a single or a few spacecraft, but an entire swarm of spacecraft that would span both fluid and ion characteristic scales that would enable us to actually track how these waves are generated and evolve at the tens to hundreds to thousands of kilometers scale. And I don't have time, but if you'd like more details, a white paper on this can be found at that archive address right there. And also Tony Case at SAO is one of the leads for actually building the instruments that would go on this swarm of spacecraft. So I'll leave you there just with the idea that properly modeling all of these different sources of free energy will significantly change the inferred growth rates and the inferred methods of transporting energy through this coupling between the fields and the distributions. And so getting a good understanding of that underlying velocity space structure is essential for understanding the turbulent processing of the energy in these weakly collisional systems. So with that, thank you, and I do apologize for the quality of the internet in Arizona.
Okay, thank you, Chris. Yeah, I think so. We managed to hear. I think you managed to just get your point across, but it was touch and go sometimes with the internet. So yeah, thank you for that. We have time for a quick question if anyone would like to raise their hand. If not, maybe I can just ask probably a naive question. So you mentioned that you only have measurements from one point in space. Is that because so where is that coming from?
Effectively, right, these are one point in space. I hope I have this in my backup. I do. So most of these spacecraft are launched one at a time. We do have measurements at many different distances from the sun. For instance, Helios went close. Probe is going much closer, but most of our measurements are made at a single point. We have a few missions like MMS, Cluster, and Themis that are constellations of, say, 4 spacecraft. But just due to cost restraints, we typically have not in the past thrown up entire swarms of spacecraft that would enable us to measure these processes that occur on tens to hundreds to thousands of kilometers.
Okay, thank you. Okay, so if anyone would like to any further questions, then I suggest to sign up for Chris's one-to-one session. And with that, I will hand over to Jason. Thank you.
All right. It's my pleasure to introduce our second speaker, Elisabeth Matthews. She did her PhD in Exeter with Sasha Hinckley, and then she was a postdoc at MIT for 2 years, working with Ian Crossfield. She's recently, in September, just started a new postdoc at the University of Geneva, working with Damien Segrinson to combine multiple planet detection techniques. And today she's going to talk to us about probing exoplanet populations and their evolution with debris disk observations. And just a reminder that we are recording this, so keep that in mind. All right, with that, I will hand it over to Elisabeth. Thank you.
Yeah, thanks very much for having me. I was meant to be speaking at Harvard almost a year ago while I was still based at MIT, and I've moved continents since then, and it's been a pretty interesting year. But it's great to be able to speak to you today instead about some of my work, primarily using direct imaging to think about both exoplanets and debris disks. So I'm going to start with the classic plot. Probably many of you have seen this plot many times before. This plot shows the roughly 4,000 planets that have been found to date. So exoplanets are common and we know about quite a lot of them, but you can see in this plot that the planets are color-coded by detection technique, and the subset of planets that have been directly imaged is pretty small. And that's both because these planets are intrinsically rare. So Brendan Bowler had a result where he found that the occurrence of the kind of planets that we can image with current facilities is less than 1%, it's 0.6%. And that's planets above a couple of Jupiter masses and more than a couple of tens of AU from their host stars. And these planets are also very hard to find. We just don't have the sensitivity to small planets that the radial velocity and transit techniques, for example, do. So although in the next decade or two, those mass limits will start to really push down. Right now, we're typically limited to planets that are bigger than a Jupiter mass with the direct imaging technique. Now, the lack of planets of this type is a real shame because these planets are so great in terms of characterization and really understanding the planets, what they're like, how they formed and how they've evolved. And I'm going to highlight just a couple of characterization possibilities for these planets on this slide. So the figure that you're seeing at the moment is the spectrum of HR8799c. This is a directly imaged planet with about 5 Jupiter masses, and all of the structure that you can see. So the black line is the spectrum and the green line is the model, and you can see there's all of this structure, and that's not just noise, that's also actually the individual molecular absorption lines, so the forest of absorption lines that you can see in that spectrum. And for example, just over here, if you can see my mouse, there's a big CO band head. Sorry about that. And we can use features like that to really constrain the elemental abundances of species like carbon and oxygen in the atmosphere of a planet like this, and thereby probe its formation and determine whether it matches the composition of the star or perhaps the composition of a part of the disk where it maybe accreted a large amount of material. Another really cool possibility with these planets is to look at their variability. So we can monitor them over time, and we can use that, for example, to determine their orbital periods, to look at how cloudy they are and how those clouds are varying over time. And Marta Bryan has been leading this really cool project where she's actually using the orbital period in combination with direct measurements of the V sin I of the planet to determine its line of sight inclination, which we can then compare with the line of sight inclination of the star and also with the spin orbit alignment. And again, use that to start to probe how these planets are forming, whether they're forming by a disk fragmentation process or by something more akin to a core accretion process. But in both of these cases, there's such a small sample of planets that we really only have individual snapshots of these measurements rather than having an understanding of the population of planets and whether orbital misalignments are common or rare. So really what we need to do is find more of these directly imaged planets, and particularly more planets that are really well suited to some of this more detailed characterization work. So in terms of the characterization, having a mass is really important as well in terms of understanding what we're looking at. Now, one of the main techniques that I've been using to try and do that is using disks as a signpost for where we should be looking for these planets. So many of you may have seen this protoplanetary disk image before. This is one of the first ALMA images that was released, and all of those dark rings that you can see in the disk are believed to be the sites of ongoing planet formation. Now, I typically think about systems that are a little bit older. So instead of being gas-dominated protoplanetary disk, we're now thinking about debris disks, which are dust-dominated. So they're fainter and they are harder to image. And on this slide, I'm actually showing scattered light near-infrared images of these debris disks rather than the ALMA thermal emission image that you're seeing on the left for the protoplanetary disk. So these disks are a little older. They're more than 10 million years old. And at those ages, the dust in these systems is relatively efficiently removed from the system. So that means that if we're seeing dust, it must be constantly regenerated within the system due to the collisional grinding of planetesimals. So planetesimals are crashing into each other and generating these large volumes of dust that we can directly detect. And it's been kind of inferred for a while that perhaps the higher rate of collisions in some systems is associated with one or more giant planets in those systems. So the gravity of the planet might be stirring up those planetesimals, causing them to crash together more often and generating these high levels of dust that we're able to see in these debris disks. That link was tentatively observationally confirmed. So there's some evidence that the occurrence rate of giant planets might be higher in debris disk systems. But because the total number of known planets of this type is still really low, those statistics are still not very strong. We really need a bigger sample to be able to confirm that correlation. And I'm hoping that the Big Sphere and GPIO surveys will be able to help us really understand that correlation in more detail. Another advantage of these systems is that just like for the protoplanetary disk, we can sometimes see structure that relates to the presence of planets in these systems. So for Beta Pictoris, it's a little hard to make out in this image, but there's an inner disk which is misaligned with the main outer disk, and that misalignment is believed to be associated with the known giant planet in that system. And then HIP 73145 down here, you can hopefully make out maybe 2 or perhaps even 3 distinct ring components with gaps in between them. So that's an architecture very similar to that of the protoplanetary disk, where there's discrete rings of dust and gaps in between them, perhaps associated with the location of planets. And I've particularly focused on these systems because we can really use that disk structure. Firstly, we know that if there's a disk, it's likely that the planet occurrence rate is higher, so we're more likely to be able to find planets. And also we can use that structure to try and constrain the location and the mass of the planets in these systems. So in terms of the location, if we're thinking about a planet clearing a gap, then if we know where the gap is, we know where the planet should be. And we can specifically target our surveys at stars where that gap between two belts of dust is far enough from the star that we should be able to resolve it with current instruments. And then on the mass side, various different people have looked at trying to run dynamical models and constrain the massive planet that we expect to see as a function of the disk properties, so the location of the two belts of dust in those systems. Sarah Morrison and Erica Nesvold both did this for a single planet case, and then in Shannon et al. 2016, we extended it to a chain of planets, clearing out a really broad gap in the disk. So you can have several planets. We assumed equal planet mass in this work, kind of spanning a really broad area, and then we can predict what massive planets we should expect to see in those systems. And I led a survey where we tried to search for planets like this. So we specifically targeted 24 of these systems where there's multiple distinct belts of dust, and we were trying to find the planets within those gaps between the belts of dust. So these images are thumbnail images of 4 of the targets from that survey. And for those not familiar with direct imaging images, the star is actually in the very center of each of these images. It's blocked out, it's behind a coronagraph, and we just zero out the pixels in the very center of these images. And then you can see there's kind of a characteristic noise pattern. So there's some noise very close to the star, and some of that flux is negative. That's where we've overcorrected for the starlight in our images. And then there's also a ring here, and this is also to do with the characteristic noise pattern of the instrument. And then all of these sources that I've highlighted with arrows are astrophysical point sources. So these are real on-sky sources rather than being contaminating starlight. And the trail that you see for some of the brighter objects is just, again, an artifact of the data reduction that we're doing here. Now, in this case, all of the point sources that we detected actually turned out to be chance-aligned background stars rather than being co-moving planet or brown dwarf objects associated with the primary stars. So we didn't actually detect planets in this survey, but we were able to place really tight limits on the parameter space. So with the combination of the location and mass constraints from the disk, and then also our observational limits, we can put a pretty tight window on where we expect those planets to be, even though we didn't find them. And we're optimistic that for some of the best suited targets to this work, we might even be able to detect those planets with the James Webb Space Telescope. And certainly the extremely large telescopes will be able to push our mass limits down and hopefully start to detect lots of these planets that are forming the gaps in the debris disks that we know are there. And a kind of additional benefit of this kind of work is that we sometimes directly detect the disks themselves. So this is an image of one of the disks from the survey. This is HD 129590. So you can see this image. This is a really bright, close to edge on disk that we've directly detected. And images like this can help us to constrain the structure even more clearly and potentially see some of those warps and gaps that we believe are associated with the planets. And then also we can study the disk directly by doing things like looking at the scattering phase function of the disk. So measuring how the disk, how bright the disk is at different scattering angles and using that to infer something about the properties of the grains. I also want to highlight another scattered light disk that we have. This is a paper which I believe we're resubmitting to the referee tomorrow following a pretty positive referee report. So this should be out really soon. This is another disk where we were surveying stars trying to search for these planets, and we happened to detect one of the disks as well. So this is a K1 star, so it's a later type host than a lot of the disks that have been directly imaged. And you can see it's a really edge on, it's a relatively faint signal, but it's a really nice edge on disk here that's also been detected in the submillimeter with IRAM. I now want to move on and discuss another survey that I just recently had published. So in this survey, we were thinking specifically about disks with really, really high volumes of dust. So in this case, we don't have constraints on the structure. We just know that the disks are really, really dusty. They have a huge infrared excess as measured by the WISE mission. And in this case, we looked at 20 stars and we did find some companions. And these are images of the 3 companions that we detected. in the survey. So the one on the right is actually a really bright companion. This is well into the stellar regime. So you're seeing an unocculted image of the stellar PSF, and then the companion is down here. And the other two images are more typical direct imaging images. So again, the star is behind the coronagraph in the center, and you see some stellar noise, and then you see the companion PSF pop out really clearly here and here. Now, one of the real benefits, I touched on this at the beginning of the talk, one of the real benefits of this technique is that spectroscopic data is relatively readily available. And in fact, the instrument that we used for this work, the SPHERE instrument at the VLT, has two backends. So we're simultaneously measuring with a wide field imager. And when I say wide field, I mean 12 arc seconds, which I know is not wide for many people, but it's a relatively large field of view for this kind of work. So we get this really broad picture of the stars. And then we also have an integral field spectrograph with a smaller field of view. So that's an instrument that's simultaneously measuring spectra throughout its field of view. And actually for both of the two companions on the left, we have integral field spectrograph data. So this is the level of spectra that we can detect, that we can extract even just from the discovery data. So this is only about 35 minutes of on-sky integration, and this was happening simultaneously to the images that you're seeing in those thumbnails. So what I'm showing here, the black points are showing you the spectrum of the companion. And I've actually replotted that several times with an arbitrary flux offset each time. And then I've also plotted the rainbow lines indicate several different reference spectra, which I've scaled to match the spectrum of the companion. And we can use that to visually determine roughly what spectral type these are. So just by matching the shape of the spectrum, we can see which kind of spectral type these companions are. So in this case, both of them turn out to be roughly M4. You can see the one on the right really clearly matches with that spectrum, and the one on the left, there's a little bit more uncertainty because the spectrum is a bit noisier and it has this kind of peak of emission that doesn't match particularly well with any of the reference spectra. So these are stellar rather than brown dwarf or planetary companions. But nonetheless, I think this really illustrates the power of this technique in terms of not just detecting, but also characterizing some of these objects. Now, the other thing that's really interesting and somewhat puzzling about this survey was that we then determined the age of all of the stars in this survey. Now, we didn't do an explicit age selection before carrying out the survey because there's quite extensive evidence that debris disks are correlated with youth. There's quite a lot of literature looking at this that shows that debris disks are more common and are also typically brighter at very young ages. So we kind of relied on the presence of these really dusty debris disks to bias the survey towards the young ages. And you can see that from this plot over here that this didn't entirely work. So several of the stars are young system. We've got lots of moving group members, for example, with ages of a few tens of million years. But there's also several older systems in this work as well. And in particular, all of those three objects where I showed you all of those three objects that host companions are slightly older. So HD 18378, we actually don't have an age for, but the star is a giant star, so it's a more evolved star. 19257 is still on the main sequence, but it's towards the end of its main sequence lifetime. And 133778 has just very recently left the main sequence. So that's kind of puzzling, both that these older systems were in our survey in the first place, and then it seems that the places that we were finding the companions were the older systems. So I'm still, my best explanation for this is that what we're seeing is something to do with, is perhaps a planetesimal belt that was relatively calm, that was very quiet, that wasn't so dusty, that recently has been re-excited and regenerated large volumes of dust again. So the plot that I'm showing you here is from a theoretical paper by Caitlin Cratter, which was looking at the orbits of planets in binary systems as the primary star evolves off the main sequence. And the white region shows the region that's stable for the planet to orbit in. And you can see as the star evolves and the primary star loses mass, the orbit becomes chaotic, and then the planet can perhaps even transfer into orbit around the other star in the binary. Now, I don't think we're seeing anything quite as dramatic as that in my systems, and certainly the stars aren't as evolved as they are in the final panel of this image, but nonetheless, perhaps something to do with those older stars, perhaps beginning to evolve off the main sequence, is causing the planetary orbit to become chaotic and re-excite or just to evolve, re-excite planetesimals in that system, and regenerate those higher volumes of dust at much older ages than we typically see them. But I'm very open to hearing other people's opinions on these as well. I'm still very much puzzled by these systems and why they have so much dust, even though they're so old. Now, for the last section of the talk, I want to kind of switch gears a little bit and talk about some work that I'm doing now, trying to think about a slightly different signpost for how we can start to find these directly imaged planets. So another signpost for which stars we should be pointing our direct imaging instruments at. And now that I'm in Geneva, I'm working with both radial velocity and also astrometry data to try and guide our direct imaging surveys. So on the radial velocity side, here in Geneva, we have the Coralie survey, which has been ongoing for over 20 years. So we can measure these really, really long period radial velocity trends and even full planet orbits. This is an example of that from Emily Rickman. So this is a 2019 paper where you can see this really lovely long radial velocity trend, which represents, the orbit actually isn't complete, but it seems to represent an orbit of around 40 to 50 years for the full radial velocity measurement. And they were actually able to directly detect this object as well. So it's this source that you can see to the right of the coronagraph. So this is actually a brown dwarf rather than a planet. It has a mass of about 40 Jupiter masses. But these measurements where we can combine both a really long-term radial velocity trend and then also a direct image of the companion are really valuable in terms of calibrating our luminosity models for brown dwarfs and planets. And in fact, there's some evidence that the luminosity masses and the dynamical masses aren't exactly matching up. So data points like this are particularly valuable in terms of trying to calibrate that relationship and tune the luminosity models to make sure that they really are correctly representing the objects that we think we're seeing. Now, on the astrometry side, I'm really excited about working with some of the Gaia data. So the Gaia time epoch astrometry isn't available yet. And actually that won't be so useful for direct imaging purposes because the Gaia time epoch astrometry will be the best for planets which are on orbits shorter than 5 years. So planets that complete a full orbit within the mission lifetime of the Gaia instrument. But the real key for direct imaging here is that we can combine the Gaia dataset with the Hipparcos dataset. So we can look at the instantaneous proper motion in the Hipparcos era and then also in the Gaia era. And if you see a mismatch between those two proper motions, that implies that as well as a long-term proper motion across the sky, you also have some planetary orbit superimposed onto that proper motion. So you're seeing small deviations in the proper motion as a function of time. Now, of course, with this technique, we only have a couple of data points. We only have the Hipparcos and the Gaia instantaneous motions and also the median motion over those 25 years. But nonetheless, that can give us some hints as to whether or not there's a giant companion perturbing the path of a star across the sky. And this slide that you're seeing here is some studies of a known planet. So this is Beta Pictoris b, where on the left you're seeing direct imaging epoch astrometry. So that's real measurements of the position of the star and the position of the companion. And then in the center, you're seeing radial velocity, and you can see this is a really noisy star. The young stars that we really like to look at with direct imaging are very noisy, so very difficult to work with in terms of radial velocities. And then on the right, you can see the Hipparcos data point and the Gaia data point. So those are two proper motion positions. And in this case, the Gaia error bar is actually really big because Beta Pictoris is too bright. It's about third magnitude in the Gaia filter. So for slightly counterintuitively, for fainter stars, we're going to do a much better job of having a really tight error bar on that Gaia position, which is going to be really constraining. So particularly in using that in combination with the radial velocity data is going to be really powerful in terms of identifying the stars that show these trends, and then hopefully directly detecting companions where we have pretty ready access to a dynamical mass, so we can really start to constrain the properties of those companions as well. I already have a small survey, which I carried out with the MAGEO instrument at Magellan, where we looked at 7 of these targets that show acceleration between the Hipparcos and the Gaia eras. And I had some really great undergrad researchers at MIT this summer, Keith Mockery and Helena McDonald, who reduced this data for me. And you can see actually 3 of these 7 targets have companions. Now, we haven't yet had a chance to study the properties of those companions, predict masses or anything like that. But this kind of demonstrates that this is a really exciting technique, and these accelerators should help us to guide our surveys and to be able to make more targeted direct imaging observations. I just want to very quickly throw up one slide completely unrelated to anything that I've talked about today. So the other half of my work, I've also been thinking about vetting some of the TESS objects. So what I'm showing in this slide is a gallery of several of the TOIs that we've actually determined to be binary or even higher order multiples. So this is a very heterogeneous set. This kind of shows you the variety of things that we found. Some of these are bound companions, some of these are chance-aligned background stars. And we've been using these both to help vet individual planet detections, and we're also in the process of writing a survey paper. So if anyone's interested in that, definitely reach out. I'd love to chat about it more offline after the talk. But I think now I'll just summarize. So hopefully I've convinced you all that directly imaged planets are really interesting. They offer a real wealth of information about planet formation and evolution. And I've explained that we need to find more of these objects. And I've talked about some of my work using debris disks to help guide our surveys, both because of the dynamical information that they give, but also because sometimes we get these serendipitous detections of the disks themselves in scattered light. And finally, I've talked a little bit about some of my more recent work, thinking a little bit more about how we can combine direct imaging with indirect dynamical methods for detecting planets. So thank you very much for listening, and I'll now take any questions.
Thank you, and let's all thank Elisabeth again. If anybody has questions, feel free to raise your hand, and then I will call on you, and you can just unmute yourself and ask. While we're waiting for people to find that button, I have a question about the combining Hipparcos and Gaia. I know that Gaia is supposed to be releasing all of their epoch photometry or epoch astrometry in DR4, I suppose. Does that already exist for Hipparcos, or do they just publish their fits, or how does that work?
I think it does. I don't think the signal to noise is high enough to be particularly useful in detecting planets, but I'm not an expert on that. I haven't dug into the Hipparcos data itself in detail, but there was actually a paper very similar to this one. Ignis Snellen led a paper where they were also trying to use Beta Pictoris to measure the mass of Beta Pictoris, and I think in that one they had individual Hipparcos epoch astrometry as well as the Gaia data point to determine that mass.
Interesting. I was just thinking if it would be better if you could combine all of the epoch astrometry from both missions rather than take a mean proper motion from both to see if they changed, and you could actually constrain a long period orbit.
Yeah, I think that would, I mean, again, I haven't thought about that in too much detail, but I think that's definitely an avenue that we should consider. I still don't have a good enough sense of the different constraints that you get from the short-term Gaia data, which gives you the time resolution, but also only does a bit of that curve, versus especially for the very long period things, I think you see so little trend in Gaia that it's perhaps sometimes better to just, if you have something on a 60-year orbit, say, the 25-year baseline from Hipparcos to Gaia is much more valuable than the 5-year tiny little bit of the orbit in Gaia. But I don't know what different parameter spaces the different combinations of data are more valuable.
Cool. Any other questions? If not, I have another one there. So how do you, what do you do multi-epoch observations, or how do you determine whether or not the background stars that you're finding are bound or not?
For the direct imaging work, we've been doing multi-epoch observations. So we basically go back a year later and see if the object has the same proper motion as the foreground star. And we specifically select foreground stars that have a high enough proper motion that will be constraining. It's also possible to do that spectroscopically. So the for very faint objects, Sphere actually images in 2 different filters, one on the methane line and one just off the methane line. So we're collecting those images simultaneously, and if the companion is faint enough that if it was bound, so if it was at the same distance as the host star, it would have methane, then we can look at whether there's a difference in the color in those two filters. So if it's a background star, it would have the same color in both filters because it's a star. And if it's a bound planet, then it's a, and it has methane, then we can detect that. But that's not so useful a lot of the time because a lot of the companions are high enough that we're not confident they'd have a huge amount of methane. And a lot of them are outside of the integral field spectrograph unit. So then we only have the two colors, which I think it's safer to use multi-epoch astrometry.
Yeah, sounds great. Jennifer, do you want to unmute yourself and ask a question?
Sure. Hi, this is Jennifer Yee. I thought it was interesting that you're searching for directly imaged companions to stars, and in general, you don't seem to be finding them. And so I was wondering if you'd like to comment or speculate on the implications of that. Like I think you've conclusively shown that you're sensitive to such things, but
Yeah.
so does the fact that you're not finding them mean that there's like limits?
Yeah. Yeah, I think that's been kind of happened across the board. Like Sphere and GPI both had predictions of tens of new directly imaged planets, and it hasn't happened. And at this point, that's not just the teams taking their time to reduce the data, that's because those objects aren't there. I think they've had one directly imaged planet from each of Sphere and GPI, and one planet that was later redacted. So yeah, that definitely, these objects are really rare, and that I think also the predictions of tens of planets for these instruments came in part from the relatively early discovery of HR 8799, which has 4 giant planets, but that's clearly a very unusual object. There aren't a lot of those planets, because if there were, we would have found a lot more of them. The optimist in me wants to say that we just need to push a little bit deeper. That I think the disks in particular show that there must be something sculpting these disks, especially when we see these complicated structure, these rings and these warps and everything. There must be stuff out there, but it's clearly still too small for us to detect. So yeah, I think there's good evidence that potentially James Webb and definitely the ELTs will push down to the masses where we start finding this stuff. But I think it's a little hard to know until we get down to the mass where we start finding lots of stuff. It's a little bit difficult to know exactly where that mass will be.
Oh, okay.
Does that answer your question?
Yes.
Yeah.
All right, great. I think we're just about out of time. So let's thank both of our speakers again, and we'll see you guys next week.
Thanks.
Thank you, everybody.
No, Chris is gone. Okay. I was going to say, Jason, do you know? Oh, let's stop that first.